Okay, so we can generalize this map of the Mobius strip to, well, actually, you know what, we'll use the whole paper. So I can say, I can put an arrow up here and an arrow down here. And what that is going to signify is connect these two arrows up the same way. So that says if you are traveling up this way, you teleport over to the other side, but you keep facing the same direction.
Yeah.
What shape would this paper turn into?
Well, just a tube, a cylinder.
A tube, yeah. And how about if I said, in addition to that, we're going to connect this side and this side the same way, so that if you're going across this way, you just teleport over to the other side over here.
Wouldn't that be a tube folded on top of itself?
So what kind of shape would that be?
Oh. It'd be sort of a weird shape, because you'd have like two openings on one side, and then closed on the other side.
Right, do you want to try to fold this up and see if you can see what sort of shape this would be? What would it look like?
So you have to create a tube,
Right, you have to create a tube.
and then you have to make the arrow, these arrows. Because you've already made these facing the same way.
Okay. What happens now?
Well, they are facing the same way, because these are both pointing up.
Alright, so our original arrows that you folded up are pointing the same way. And what about our other two arrows now?
Well, are they pointing different ways?
Are they pointing the same way or are they pointing different
I
ways?
think they're pointing the same.
Yeah.
Okay. So what would you do now if you could?
Well,
I'd just fold them on top of each other.
but they're already the same way. So
Okay.
do you need to do anything?
Well, no, it
They
means
need
that
to line up.
they need to line up with each other.
So you need to kind of fold it over.
Yeah. And what sort of shape would we end up making if you folded that over?
Well,
You have to pretend it's sort of made out of Play-Doh or something so that you could...
Well, wouldn't you make a torus?
Okay,
Because
why?
you'd have to make these two ends meet,
Alright.
and that gives you sort of like a bagel shape.
Okay.
Bagel.
And look what I happen to have, just by total coincidence, with me here.
bagel.
A bagel. Okay. So you can kind of imagine you make your tube, and then you just sort of bend it around and connect up those sides, and we get. Can you see how that makes this bagel?
Mm-hmm.
Yeah.
But there's one interesting problem.
Well, you have this hole.
You do have a hole. You do have a hole. That's not really a problem.
Yeah.
The problem actually relates to geometry. In this setting, in our non-bagel setting, the distance from here to here and the distance from here to here is the same.
Yeah.
Right? And you see that on the cylinder. The distances are the same.
But then when you stretch it,
But on the bagel, you have two distances that are not end up not being the same. See, when you bend the cylinder around, the inside circle, which is one part of the tube here, and the outside circle, what can you say about those two circles?
well, they're different radii.
Yeah, they're not the same size.
Otherwise, you'd have just a circle.
So this is a good representation of a torus, and this is actually when you usually hear about a torus. This is the
Bagel.
shape that people make
Or a
some-
donut.
Yeah, bagel, donut. See, people aren't very creative. That's what you usually hear about a torus.
So too.
But it doesn't have the same geometry as this, because the circles have two different distances, and on the piece of paper here,
They have the same.
they're the same.
Hmm.
So people wondered for a long time, mathematicians wondered for a long time, was there a way to make a torus shape that was where the distances got preserved, where the straight lines got preserved, where the geometry got preserved? I'm probably not saying it exactly right. And that's the shape you guys looked at this morning.
Cool.
So hold on for a second.